graphs of rational functions. So we get some review today with the horizontal and vertical asymptotes that we've been working with, and we're putting them in conjunction with several other things that we already know how to do to see how we can use them to graph rational functions. Now, we can graph anything on the face of the earth if we just plot enough points, but there are some drawbacks to that, right? Like, plotting points is not the fastest, most efficient way of doing something. And sometimes our graphs are so elaborate we end up having to plot like 15, 20 points in order to get an accurate graph, and a lot of those are decimals and fractions that we're having to work with. And then sometimes we still don't come up with an accurate graph even after we've done all of that work. So we want to use some other resources to help us with that. And so on page 199, they suggest to me 7 different things that I can put together to help me with my graphing of these rational functions. Now, yesterday we talked about our definition of a rational function, and we said that it was going to be one polynomial divided by another where they had no common factors. So something like what we see here, 3 over x minus 2, okay? So the first thing they're going to suggest to me is that I find my x and my y-intercepts. If I'm graphing something normally, those are usually the first points I find, right? I'll go through and put 0 in for x and 0 in for y and find my x and y-intercepts, some of the easiest points to find. So to find our y-intercept, we would just put 0 in the place of x. So if we come up here and we put 0 in the place of that x, what are we going to get? 3 over negative 2. So negative 3 halves for our y-intercept. So we can go ahead and plot that point, 0, negative 1.5 for our y-intercept. To find an x-intercept, we usually put 0 in for y. And we actually can simplify that down even further with a fraction, because if you want to know where this fraction is equal to 0, because of course g of x is y, so if I'm putting 0 in for y, I'm putting 0 in for g of x. I want to know where that whole fraction equals 0. Where's the only way that a fraction can equal 0? What's the only way a fraction can equal 0? If 0 is in the numerator. Yeah, anywhere your numerator is equal to 0, your fraction is going to be equal to 0. So we can say, okay, for our x-intercept, typically we would put 0 in for y, but we can make that even a little simpler and say, let's just set our numerator equal to 0. So in this case, my numerator is 3, and if I set 3 equal to 0, 3 doesn't equal 0. So that just means I don't have 1. That's still going to be helpful information, though, to know that there's nowhere my graph crosses the x-axis. All right, then we go back to horizontal and vertical asymptotes that we've been working on. So for our vertical asymptotes, of course, we set our denominator equal to 0. So let's take our denominator, which was x minus 2, and set that equal to 0. And that'll give us a vertical asymptote at x equals 2. Also remember that when you write a horizontal or vertical asymptote, don't just say 2. You do need to say x equals 2 or y equals 2, whatever the case might be. 2 is a point, x equals something, or y equals something is a line. So there's our vertical asymptote at 2. All right, how did we find our horizontal asymptotes? Yeah, we compare n and m, the degree of the numerator with the degree of the denominator. So what's the degree of our numerator here? 0. That one's a kind of tricky one, because if you look at it, I just have 3. There is no x there. That's 3x to the 0. If it were 3x to the 1, there would be an x to the first power sitting there, right? And remember that anything to the 0, other than 0, anything to the 0 is 1. So if I have x to the 0 here, that's just 3 times 1, okay? So yeah, the degree of my numerator is 0. What's the degree of my denominator? 1. So since the degree of my numerator is less than the degree of my denominator, am I going to have a horizontal asymptote? Yes. What is it? Y equals 0. Yes. So let's go ahead and graph our horizontal asymptote as well. We're going to have a horizontal asymptote at y equals 0. A little later on in the lesson, we'll talk about a slant asymptote. A slant asymptote is exactly what it sounds like. It's an asymptote. It's not horizontal. It's not vertical. It's slanted. If you have a horizontal asymptote, you will not have a slant asymptote. So you're either going to have number 4 or number 5, one or the other. Since I had a horizontal, I'm going to skip right over number 5 because there's no way I'll have a slant. So when we get to one that doesn't have a horizontal, then we'll talk about how to know if we have a slant and how to find that. All right, so then the next thing, number 6, says go back and plot points now that you kind of have some guides. Go back and plot points to fill in any graphs, to fill in any gaps that you have in your graph. Here's the main thing I want to stress to you about this. You will have a part of your graph on both sides of every vertical asymptote. What's really frustrating is when you go through all of these steps and all of this work and you only fill in the graph on this side and you forget to come over here and fill in the graph on this side, and you lose half the points on the whole problem because you only graphed half the thing. Okay? So be sure that you graph on both sides of a vertical asymptote. All right, so let's start over here then on the left-hand side and see if we can figure out what's going on with this graph. Here's what I know. I know that I have a Y-intercept right here, and then of course I've got my asymptotes. Looking at that, I know that as I approach an asymptote, my graph is going to get closer and closer and closer to it and not touch it. And the same thing as I approach this asymptote down here, it's going to get closer and closer and closer to it and not touch it. So honestly, I have enough information to draw half of my graph right now, where I could look at this and say, okay, I've got this point, so that tells me where this portion of the graph is going to be, and I have to approach those asymptotes, so this portion of the graph is going to look like this. But just to make me feel a little bit better, maybe I want to give myself another point or two just to make sure I'm on the right track. So since I have this one point right here at 0, maybe I want to give myself a point at +1 and -1. So I could go through and plug in +1 and -1 into my function and get the y values associated with them. And then sure enough, that reinforces exactly what I thought the graph was doing. If I have these 3 points right here, when I connect them, then I can see, okay, yeah, I'm going to come up here and approach this asymptote, and I'm going to come down here and approach this asymptote. That's exactly what that portion of my graph is going to look like. All right, then we also know that there's going to be a portion of my graph on the other side of the vertical asymptote. So let's come over there and look at what we've got. I don't have anything. The only thing I have are my asymptotes, which will be guides for me, and the fact that I don't have an X-Intercept, so I know that I'm not crossing over here. Well, you can't cross over there anyway because there's an asymptote there. You can never cross an asymptote. We get that idea, but you can cross an asymptote. Yes, it is typical asymptotic behavior for a graph for your function to get closer and closer and closer to the asymptote and never cross it. But that does not mean that your graph cannot cross over your asymptote. I have seen lots of different functions. Let's say that you had something that looked like this. I've seen lots of them where, you know, like you had an X-Intercept right there. Well, my X-Intercept is sitting right there on my asymptote. So I'm obviously going to cross that asymptote. And, you know, it would end up doing something like this where it would approach each of those asymptotes, but it would cross that horizontal asymptote. I've also seen other things like the function, you've got an asymptote running here and the function crosses over it and then comes back down and approaches it. Or I've seen all kinds of craziness where, like, you've got your asymptote here and your function crosses over it an infinite number of times, and it is continually approaching that asymptote and getting closer and closer and closer to it, but it is crossing over it. So we don't want to think that we can't ever cross an asymptote. We can, although it just is not typical behavior for our function to do that. So, if I go back to what's going on the right-hand side, of this function over here, I'm definitely going to need at least a point or two to see where I am. So since the asymptote is at 2, let's maybe plug in 3 and 4, okay? So I'll plug in 3 and I'll plug in 4. And once I have those 2 points, then I have a really clear indicator of what's going on. Because if I were to connect those 2 points right there, I'm going to come up here and approach my asymptote, and I'm going to come down here and approach my asymptote. So then I can see what that piece of the graph is going to look like. And we have a nearly flawless graph with just 4 points. Whereas if I didn't have those asymptotes and those other guides to help me, if I start graphing this, typically we make an XY chart and we put in, 0, 1, 2, 3. I put in 1 and I get -3. I put in 2 and I get undefined. I put in 3 and I get +3. I don't have a clue what is going on with that function. So I'm going to end up having to go back and put in a whole bunch of points in between -1 and +1, and guess what? They're all going to be fractions and decimals and miserableness to plug in, right? So definitely a much simpler route to go to use these other resources. All right, let's look at another one. Example number 4. We said that we always want to make sure that we don't have any common factors. So the first thing I'm going to do is factor my numerator and denominator and make sure I don't have a common factor that would cancel out. I'm not wasting my time because I'm going to end up having to set the numerator and denominator equal to 0 eventually for other stuff anyway. So if they're already factored, it'll save me time then. All right, so number 1, we said let's find our X and Y intercepts. All right, to find our Y-intercept, what do? Set X equal to 0. Right, so let's go through and let's put 0 in the place of X. So that would be 2 times 0 minus 3 times 0 plus 3. So 2 times -3 times +3. And then down here, 0 minus 2, 0 plus 2. That'd be -2 times +2. So we're going to end up with 9 halves. So there's my point right there, 0, 9 halves, or 0, 4 1/2, however you want to think of that. All right, how do we find the X-intercept? Set Y equal to 0, right. And because this is a fraction, what's the only way my fraction can equal 0? Yeah, if my numerator equals 0. So let's let the numerator equal 0. So if you come up here, can 2 equal 0? Not the last time I checked, so let's toss that out. X minus 3 equals 0 would give us X equals 3, and X plus 3 equals 0 would give us X equals -3. So 3 and -3, let's go ahead and plot those. X-intercept at -3, X-intercept at +3. All right, then we want to find our asymptotes. So let's start with vertical asymptotes. How do we find those? Set your denominator equal to 0. All right, so we've already got our denominator factored. If we set our denominator equal to 0, what are we going to get? X equals 2 and X equals -2, right? And again, be sure that you're writing those as X equals 2 instead of just 2. X equals -2 instead of just -2. 2 and -2 are points. X equals 2 and X equals -2 are lines. You will lose points for those on the test if you don't have X equals with it. Same thing with your horizontal asymptotes if you don't have Y equals with it. All right, so we could go ahead and put our asymptotes on, a vertical at +2 and a vertical at -2. All right, then for our horizontal asymptote, what's the degree of your numerator? 2. What's the degree of your denominator? So if the degree of the numerator and the degree of the denominator are the same, then remember that we do leading coefficient over leading coefficient, right? So leading coefficient here is 2. Leading coefficient here is 1. So we'll have Y equals 2 over 1 or Y equals 2. So let's go ahead and graph that one as well. Horizontal asymptote at Y equals 2. if you have a horizontal asymptote, can you have a slant asymptote? No, so let's skip that for right now because it's not applicable. And then we'll go to number 6, which is plot whatever points we need to on our XY chart to fill in any gaps, being sure that we check both sides of every vertical asymptote. You are going to have a piece of your graph here, and here, and here. So I need to make sure that I have a graph in all 3 of those places on both sides of each of my vertical asymptotes. All right, so let's start all the way over here to the far left. All the way over here on the far left, I have this point right here, and I have the asymptotes. That's honestly all I need to sketch that portion of the graph. Because I could look at that point and say, okay, I'm down here below the asymptotes, I'm not up here. If I'm down here, I'm going to approach this asymptote and I'm going to approach this asymptote. So basically my graph is going to look like that. But just to make myself feel better, I could give myself another point or 2 just to reinforce that concept. And so sure enough, I had the point -3, so maybe I come over and give myself -4. And once I have those 2 points, then it reinforces that thought that I had of what that piece of the function looked like approaching those 2 asymptotes. Earlier in the year, we talked about even and odd functions in symmetry. They don't talk about it here in our textbook at this point. At least they don't go into great depth about it. But if you were to recognize that this was an even function, right? The way that we did that before to test for even or odd was we put a -x in the place of x in our function. And if you get the exact same thing you started with, it's an even function. Even functions are symmetric with respect to the y-axis. That means that if you fold your function on the y-axis, it folds on top of itself. An easy way to spot that in this function is that every x value in this function is raised to an even exponent. So if I put a -x in the place of each of those x's, I'm just going to go right back to what I started with, right? Why is that worth my time and energy? Because if I find out that this function is symmetric with respect to the y-axis, that basically it would fold on top of itself, I literally just cut my work in half. Because if I figure out what this half looks like, I automatically know what this half looks like because it's just the reflection, right? So that would be a really powerful tool. And we see that if we come over here to this side and say, okay, I had this one point and I kind of get the idea that it might do this. If I want to double check myself, I plug in a +4 and then it really jumps out at me because I get the exact same y value as when I plugged in -4. So remember that when something was an even function or when it reflected in the y-axis, when you put in a -x, you got the same thing for y as when you put in a +x. And we see that there. So in any case, whether I plotted the points or whether I recognized the symmetry and used the idea of reflection, I'm going to get the exact same type of image over here as I did over here. So then that just leaves the piece in the middle. And here's what I know about the piece in the middle. I've got the asymptotes and I've got that Y-intercept right there. I'm definitely going to need some more than that. So since that's at 0, maybe I want to come in and give myself a value at +1 and -1. If I had recognized that symmetry previously, then I would know, hey, I'm going to get the same Y value for +1 and for -1, so I can just plug in 1 point and get 2 for 1. But whether I plug in +1 or -1 or both, I'm going to get 5 1/3. So once I have those 3 points that I can connect, then I know what that piece of the function is going to look like because I can connect those and then approach my asymptotes. Connect those and approach my asymptotes. I don't want to begin to think about how many points I would have had to have plotted to get that accurate of a graph. Easy 30, and easily most of them being fractions and decimals, and I'm still going to have a really hard time telling exactly where this levels off or exactly how, where these asymptotes are here. that type of thing. All right, let's look at another one. We've been talking about the fact that you will not have a horizontal asymptote and a slant asymptote at the same time. Okay, so when will I have a slant asymptote? You will have a slant asymptote when the degree of the numerator is exactly one more than the degree of the denominator. You'll have a slant asymptote when the degree of the numerator is exactly one more than the degree of the denominator. With horizontal asymptotes, what happens when the degree of the numerator is more than the degree of the denominator? Then there's none, right? You don't have one. So that's how we know you won't have a horizontal and a slant at the same time. If the degree of the numerator is larger than the degree of the denominator, you're not going to have a horizontal. So that means, hey, I better stop and check because I might have a slant. So check and see if the degree of the numerator is exactly one more than the degree of the denominator, then you are going to have a slant asymptote. Now, we mentioned a slant asymptote is exactly what it sounds like. It's an asymptote that's not horizontal, it's not vertical, it's slanted. How do I find it? I'm literally going to divide. If I have f of x is equal to x squared minus x over x plus 1, the degree of the numerator is 2, the degree of the denominator is 1. The degree of the numerator is exactly 1 more than the degree of the denominator, I will have a slant asymptote. Here's how I find it. I'm literally going to divide x squared minus x by x plus 1. Now, I'm not really sure why I did polynomial long division because that is not the best way to do this. I'm dividing by x minus k, right? So I could do synthetic division where I put my little -1 in the box and I copy my coefficients across the top. And I could do my synthetic division, right? That would be so much easier. And that would still give me the 1x minus 2 with a remainder of 2, right? Much faster and easier way of doing that. Whichever way you do that, once you divide, your slant asymptote will be the answer that you get ignoring your remainder. So your slant asymptote would be the answer that you get, x minus 2, ignoring your remainder. Now, a slant asymptote is an equation, right? So I'm going to need to take the answer that I get, x minus 2, and set it equal to y, and then I literally would graph y equals x minus 2. It's going to be a slanted line. That's my slant asymptote. So let's do an example from start to finish that does have a slant asymptote in it since we've not seen one of those yet. So look at example 5. Different equation than this one we were just working on here. That was just for an example of a slant asymptote. So for example number 5, we're going to start off making sure we don't have any common factors that we could eliminate. And we don't, so it's in lowest terms. So what you want to start with? All right, x and y-intercepts, putting 0 in for x and 0 in for y, right? Okay, so when we were doing these before, we did the y-intercept first. So we put 0 in for x. So if I put 0 in for x, I'll get -2 times +1 over -1. So that would give us +2. So go ahead and plot that point, 0, +2. There's my y-intercept. All right, how do we find the x-intercept? How do we find the x-intercept? Close. Yeah, we're going to set y equal to 0, and in a fraction, the only way the fraction equals 0 is when what equals 0? The numerator equals 0, right? So we said there's a little bit of a shortcut there that we could think of it as setting the numerator equal to 0. So it's already factored. If we set this equal to 0, we'll get 2. If we set this equal to 0, we'll get -1. So let's plot those. X-intercept at 2, x-intercept at -1. All right, then asymptotes. How do we find vertical asymptotes? Denominator equal to 0, right. So that'll give me x equals 1. So let's go ahead and plot that vertical asymptote at x equals 1. Horizontal asymptote, I'm going to need to compare the degree of the numerator and denominator. What's the degree of my numerator? 2. What's the degree of my denominator? 1. So when the degree of the numerator is larger than the degree of the denominator, what do I know about a horizontal asymptote? There is not one, right? If I don't have a horizontal, then I need to check for a slant. And I'll have a slant when the degree of the numerator is 1 more than the degree of the denominator, and it is here. The degree of the numerator is 2, the degree of the denominator is 1. I am going to have a slant asymptote. So the way that I find that is I literally divide. So again, I wouldn't have to do polynomial long division here. I definitely could do synthetic division and get the same thing. And my answer for my slant asymptote is going to be the answer that I get when I divide, ignoring the remainder. Take that and set it equal to y. My slant asymptote will be the answer that I get when I divide, ignoring the remainder, set that equal to y, and that'll be our slant asymptote. Now, we know what y equals x looks like. That's one of those 6 graphs that we had to know from page 100. So let's go ahead and graph that. And I'm just going to draw it dotted instead of solid since it's an asymptote like we've been doing with our horizontal and vertical as well. Okay, so now we're ready to graph. Remember that you are going to have a portion of your graph on both sides of the vertical asymptote. So I'm going to have some over here on the left and I'm going to have some over here on the right. So let's start on the left. On the left, I have these 2 points, so I could connect these 2 points, and I'm going to approach those asymptotes. I don't really need anything else, right? I mean, that's all I need. If I connect those 2 points and I approach those asymptotes, I know exactly what that half of the graph looks like. All right, well then let's come over here to the other side of the vertical asymptote. I have this point right here, so it might make me feel a little more comfortable to have like one more point. So since this one's at +2, maybe I want to give myself a +3. So if I plug 3 into my function, I'll get 2. So plot the point 3, 2. And once I have those 2 points, when I connect those, I'm going to approach the asymptote up here and approach the asymptote down here. And I'll know what a half of the graph looks like. So again, a nearly perfect graph in just 1 point. Whereas otherwise, we could have sat here and plotted 20, 30 points, mostly decimals and fractions, and maybe still not come up with as accurate as a graph as we got here.